Some limits look hard, as is the case of this example, the limit as x goes to pi over 2 of cos 2x log base x of 3 all over 2 to the 2x. However, they follow rather systematically. So recalling some of our trigonometric, log, and exponential identities, we could rewrite that as written here. Now, imagine we could push limits through quotients. We could also push limits through linear combinations and products. Imagine further that we could push limits through powers. And finally, imagine there were some basic limits that we were free to use. Life would be good, and that's what this lecture is about. Let's start. Our initial goal is to find ways to break down limits into computable pieces and then recombine it in order that we can come up with more complicated limits. And the first thing to do is to recall, what does a limit mean? So the limit as x goes to a of f of x being equal to L, that means that the limit from the left and the limit from the right both exist. In other words, the limit as x approaches from below but is not equal to a of f of x is L, and the limit as x approaches a from the right of f of x is also equal to that same number L. We can use this definition in our monotonicity law to establish some basic limits. In particular, we can establish that the limit as x goes to a of 1 is just 1. And that would be for any a. The limit as x goes to a of x is equal to a. The limit as x goes to a of the exponential function b to the x is b to the a. The limit as x goes to a of log base b of x is log base b of a. The limit as x goes to a of sine x is sine a, and similarly for cosine. Notice in all these cases, to obtain the actual limit, we just substitute in x is equal to a. So the limit as x goes to a of f of x is equal to f of a in all these basic limits. This is not always the case. Indeed, f need not even be defined at a in some cases. Let's put that point aside for now and instead look at an example where we establish the basic limit for sine. So let's in particular look at the limit as x goes to 0 of sine x. So in this case, a is 0. So in this graph, we've plotted the sine curve around the origin, and we need to look at the limit as x approaches 0. First, from the left or from below, equivalently, and then next from above. So from the left, in this case, we've marked with these arrows, and we can clearly see that sine is increasing as x approaches 0 from below. And this means that we only need to consider negative x close to 0. We can also see and draw in here that 0 is an upper bound. In fact, it's the tightest upper bound. And we can zoom in and check this. Therefore, since sine x is increasing as you approach 0 from the left, with the tightest upper bound being 0, the limit as x goes to 0 from the left of sine x is 0. The situation for approaching 0 from the right is similar, except for we're actually decreasing, and that's because we're traversing this increasing function in the reverse direction, as shown here with the arrows, and clearly the tightest lower bound in that case is also y is equal to 0, and hence the limit as x approaches 0 from the right of sine x is also 0. And so combining these two pieces, the limit as x approaches 0 of sine x is 0. Now, as a practical matter, it's pretty much impossible to repeat all of this effort for every single function of interest, especially when monotonicity is less obvious. So we derive this basic plan. We assume some basic limits, and then we use limit laws to derive the limits of other more complicated functions. The starting point for the limit laws is two existing limits, the limit as x goes to a of f of x and the limit as x goes to a of g of x. However, for the power law, we'll also need a non-negative constant p, and for linearity, we'll need two real constants b and c. Then the limit laws collectively say that the following limits exist, and they're evaluated as follows. The linearity law in English says the limit of a linear combination is a linear combination of limits. In mathematics, this becomes the limit as x goes to a of b times f of x plus constant c times function g of x is equal to b times the limit as x goes to a of f of x plus c times the limit as x goes to a of g of x. Let's take a simple example. The limit as x goes to 1 of 4 times 3 to the x minus 2 minus log base 3 of x. Well, we'll recognize each one of these functions, 3 to the x, 1, and log base 3 of x, as basic function limit. And we'll also recall that we can just substitute the value a is equal to 1 into each of them to get those ones. And they all exist. Now there's a slight twist here because there's 3 terms and the linearity law is only for 2. However, you could apply it twice to handle 3 terms. So then by the linearity law, this limit is 4 times the limit as x goes to 1 of 3 to the x, and this basic limit is 3 to the 1, minus the limit as x goes to 1 of 2, which is just 2, minus the limit as x goes to 1 of log base 3 of x, which again is a basic limit, and it's found by evaluating log base 3 at a is equal to 1. Now 4 times 3 to the 1 is 12, and then we subtract the 2 from the second limit, and then we subtract the log base 3 of 1, which is 0, and so we wind up with 10. The product law is similar. It says in English the limit of a product is the product of limits. Reducing that to mathematics, it says the limit as x goes to a of f of x g of x is equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x. Let's take a simple example. The limit as x goes to minus pi of the natural exponential of x times the natural log of x times sine of x. Well, again, we can apply the product rule to more than 2 factors. So we could write this as the limit as x goes to minus pi of the natural exponential times the limit as x goes to minus pi of the natural log times the limit as x goes to minus pi of sine x. At this point, we realize the limit as x goes to minus pi of sine x is a basic limit, and so it's evaluated as sine of minus pi, which is equal to 0. We know the other 2 exist. We don't even care what they are, since we have the product of 3 numbers, one of which is 0, so the overall limit is 0. Next we move to the power law, which is also similar. It says the limit of a power is the power of a limit. Reducing this to mathematics, it says that the limit of f of x to the p is equal to the limit of f of x all to the p, provided that f of x is greater than or equal to 0 for all x near a. Let's take an example. Get the limit as x goes to 0 of the absolute value of x. That's the limit as x goes to 0 of the square root of x squared. And then we can use the power law twice to bring the limit first inside the half root and then inside the square. And so the result of that is this is equal to the square root of the square of the limit as x goes to 0 of x. But the limit as x goes to 0 of x, that's a basic limit, which is also 0. And you square it, you still get 0. You square root it, you still get 0. The final law, the quotient law, also has a restriction. In English it says, the limit of a quotient is the quotient of the limits, provided that the denominator limit is not 0. Converting this to mathematics, the limit as x goes to a of f of x over g of x is the limit as x goes to a of f of x over the limit as x goes to a of g of x, provided that the limit as x goes to a of g of x is not 0. So let's take an example. The limit as x goes to pi over 4 of cos to the minus 1/2 of x, well, cos to the minus 1/2 of x is 1 over cos to the 1/2 of x. And so we could push that limit through by the quotient law, provided that the denominator limit is not 0, which we'll see it isn't. And so doing so, we have the limit of 1 on the top, which of course will turn out to be 1. On the bottom we have the limit as x goes to pi over 4 of cos to the 1/2, which we can use the power law on to bring the limit inside the 1/2. And so we're left with 1 on the numerator and the limit as x goes to pi over 4 of cos x all to the 1/2 on the denominator. But this is a basic limit. So the limit as x goes to pi over 4 of cos x is just cos pi over 4. And that's 1 over root 2. So we have 1 over root 2 to the 1/2, which is 1 over the 4th root of 2 with 1 on the numerator. And the result is the 4th root of 2. Now all these laws that we've done actually also apply to just one-sided cases. So we can scroll up and put positive signs here to indicate limits from the right, or alternatively we could have put negative signs to indicate limits from the left. And in fact, we can even take a is equal to infinity when we're doing limits from the left, and take a is equal to minus infinity when we're doing limits from the right, and all these laws are still true. The polynomial and rational laws are just applications of the limit laws and the basic limits. The polynomial law says, suppose f is a polynomial and a is a real number. Then the limit as x approaches a of f of x is equal to f of a. Now this just follows by the linearity and product laws and the basic limits. To motivate the rational function law, let's take a look at the following example. Find the limit as x goes to 0 of x cubed minus 1 over x minus 1. And the numerator, f, is x cubed minus 1. And the denominator is x minus 1. The limit as x goes to 0 of g of x, x minus 1, is equal to minus 1. And that's not 0. So the quotient law applies, and we can just push the limit through the quotient. So the limit as x goes to 0 of x cubed minus 1 over x minus 1 is equal to the limit as x goes to 0 of x cubed minus 1 over the limit as x goes to 0 of x minus 1. And then by the polynomial law, we can just plug in 0 into the numerator and the denominator, and we find that this limit is 0 cubed minus 1 over 0 minus 1, which is just 1. However, if we look at the limit as x goes to 1, we find that the denominator, the limit as x goes to 1 of g of x, that's equal to 0, and the quotient law does not apply. Moreover, we could notice that the limit of the numerator, the limit as x goes to 1 of f of x, is also 0. So we have this type of 0 over 0 race, which we do not know how to handle yet. So we'll put that aside for the moment, but we'll move on to the rational law. So suppose that f and g are polynomials and a is a real number and g of a is not equal to 0. Then the rational law says that the limit as x goes to a of f of x over g of x is just equal to f of a over g of a. And this is by the quotient and polynomial laws. Now for this bad case of a rational function f over g, where the limit of g is 0, in other words, g of a is equal to 0, we would say that this rational function has a pole at a. Which brings us to our final warning. Whenever we have this situation, the limit as x goes to a of f of x over g of x, and the denominator limit is actually 0, we have to be careful. What we're going to see later is anything could happen. The limit could still exist, or we could have divergence, or the limit from the left and the limit from the right could both exist but be different, so the limit doesn't exist. So let's finish with the take-home messages. The limit as x goes to a of f of x is equal to f of a if f is a polynomial, rational with no pole at a, exponential logarithmic if, of course, a is greater than 0, so it's in the domain, sine or cosine. Secondly, we use linearity, product, power, quotient, limit laws to break down and compute limits. However, we cannot handle situations where the limit as x goes to a of f of x over g of x, but the denominator limit is 0. We could also not handle situations where we have the limit as x goes to a of f of x minus g of x, but both of those are infinity. We can also not handle the limit as x goes to a of f of x over g of x when both the numerator and the denominator limits are infinity. There are other cases we also can't handle. However, we'll focus on these three and in following lectures come up with methods to handle them. Now it would be a good idea to go back to the beginning of the lecture and look at the motivating example and look at the steps that were used.